Welcome everyone. Today we're going to be studying characterizing network traffic. This is your network design class. This is session 5. Now we're going to discuss network traffic factors. We're going to talk about network traffic flow. We're going to talk about location of traffic sources and data stores. We are going to briefly discuss traffic load and traffic behavior. And we also going to discuss about the quality of service requirements. Now, why is it important to understand your traffic flow? Now, understanding traffic flow allows engineers to better design the network by optimizing quality of service and improving the current network infrastructure. Now, we have a picture here. This was actually supposed to be a video, but this is just basically describing a chaotic situation. So as you guys can clearly see here, there is no demarcation for anything. The cars, they don't know where to go. They have no idea if that's a one-way or if that's a two-way road or if that's a two-way traffic. There are no traffic lights whatsoever. It's just basically chaos everywhere. All right. Now, if there is no traffic characteristics in here, no one knows what to do. No one knows if they should be going straight ahead or backwards. People have no idea what to do. They will not arrive at the destination on time. I can guarantee you that. And the chances of a collision, of an accident, are much, much higher than if we had everything organized, if we have traffic lights, if we had, the signs, if we had everything, the paintings on the pavement and everything else. Okay. Now, can I get a few suggestions? I think most of you guys actually drive or have a driver's license or have ever been driven somewhere and you have paid attention to traffic conditions that we have here in Canberra. Can you just basically tell me a few characteristics of what you would consider to be an organized traffic? What should I do, in other words, to make these organized, to make sure this will actually works optimally instead of just having these chaotic situation here that no one knows where to go? As you can see here, if someone wants to turn left from here, are they able to do it? It's not clear if they can do it, if they cannot do it. It's just a whole bunch of mess, right? Yeah, some people are saying lanes, traffic lights, what else? Roundabouts. There are a whole bunch of things that we can do here in order to make sure this traffic is organized. We can divide in lanes, right? So we can divide few lanes, maybe 2 lanes on each way. So in this way here we could have 2 lanes. Here we could have 2 lanes. We could maybe have a roundabout if that's the case. If we have enough room to have a roundabout here. We could have traffic lights, to tell people that they should wait a little bit before they try to do something. We could have many things here to help optimize this situation. Now, when we talk about computer networks, guys, what I want you guys to keep in mind is that we want to do the same. Okay, so we need to characterize the traffic. We need to know, is traffic going out of the network? Is traffic coming into the network? Now, which type of traffic is preferred? Which type of traffic should be given preference or precedence in the network? Who should be going first? Who should wait a little bit more? Now, we want to basically make our computer networks organized as well. We want to make sure we can transmit and receive data in an optimal way. So in order to do that, the first step that we need to do is characterize the traffic so we can understand the traffic flow. Okay. Now, when understanding the traffic flow, one of the first few steps that we need to take is understanding the user communities. So basically understanding what type of users we have in our network. Now, when we discussed the previous example in this image, we basically discussed that we need to understand what type of traffic it is, who is going where are they coming from, this sort of thing. Now, in here, when we talk about user communities, we need to understand and we need to group the communities based on the usage. So are they all trying to access a specific application? Are they all trying to access a specific server? Can we characterize them? Can we call them a user community? Now, for those people that actually studying scaling as well, scaling networks, we also discussed about VLANs in scaling networks as a way that we can segment our networks in a way that we can reduce the broadcast domain size. Now, I've also mentioned, if you're my student, scaling networks as well, that we can basically divide VLANs based on the type of users. For example, we can have a VLAN for the human resources department. We can have a VLAN for our IT department, and so on and so forth. Now, VLANs are one way we can usually group people together based on the characteristics of the applications that they used, based on the departments that they are part of. And this is exactly what the user community sets will be all about as well. Now, I'm just going to read the definition. The user communities, they are a set of workers who use a particular application or group of applications. These could be corporate departments or a set of them, for example. So in other words, if they have something in common, if they access a specific application, for example, such as SharePoint, if they access something else on the network, and they all use it for a common goal, or if they all want to achieve the same thing by using that certain application, they can be called a user community. When understanding the user communities and dividing our network based on the user communities, we also need to understand the size of the communities. In other words, we need to know the number of users. It's also important to find out if they are scattered around the locations or if they are in confined to the same physical location. This is something else that is useful for us to understand. The applications used by them is also one more important factor that will help us design our network. So this is just one example of how a table would look like, of how we could build different user communities, different user community sets, and how we could characterize them using an Excel spreadsheet, for example. So you can basically start your own Microsoft Excel spreadsheet. This is just a suggestion. Of course, you can make your own adjustments to the table if you think there's something else which is important to mention that is related to the community name. You can also list that as well with one more column and so on. How about the data stores? Now, the definition of a data store is that the data store or data sinks, they are areas of the network where application layer data resides. Examples include server farms, SANs, mainframe or tape backup units, and so on. So the data stores are basically a specific place in our network where we are going to be storing our data, our information. Now, when we're characterizing traffic, it's crucial and it's really important for us to understand where the main sources of data are located. In other words, where are the main sources of information in our network? It could be that the main data store is the internet itself, so it could be a server on the cloud, for example, in the Azure infrastructure or AWS infrastructure. Now, under some circumstances, some companies they actually choose to have a data store uh, on campus, so they actually have a server located within the premises. So on the premises data stores, they are usually connected to the network as well. So they usually a server which is attached to the network. So in order for us to determine the traffic, we need to find out where our data stores are located in the network. And of course, we need to take care of the bandwidth requirements to the data stores, because obviously we expect to have higher bandwidth requirements whenever we want to be connected to a server, because multiple users could be taking advantage of the server at the same time. Now, if you guys remember what the infrastructure that we have on campus in the ICT department. We actually have a server room in the ICT department. The server room is located right next to my office. So if you know where my office is, we actually have a door right next to my office on the right side, opposite to the side where the male's toilet is. That's where we have our internal servers of the ICT department, and it's basically where one of our Norseman and librarian public servers are located. So every time you guys try to access the ICT servers in order to reimage your hard drives, for example, or if you want to download a software from one of the classes that you were taking, you're just going to try to access the server that we have on the premises. That server would be considered to be a data store. Now, when we're describing our network design, we need to understand where the data stores are, the physical location, the applications that they're running, and which user communities are taking advantage of them in order to understand who are going to try to access those resources, if they're going to try to access the resources at the same time or not, and so on and so forth. Now, before I move on, do I have any questions so far about user communities and data stores? If not, we can move on. So just a quick review of everything we studied so far. We studied about the importance of understanding the user communities. So we basically divide the groups of users that are trying to access the resources across everything we have connected to our network. We also have the data store. So we just basically describe what a data store is, the importance of a data store, and the importance to understand the type of users that are utilizing and requesting access to the data stores. Now, guys, if we understand the user communities, we understand the data stores, and we understand the traffic flow based on the user communities and the data stores, we are actually able to make smart decisions when we are designing a network. So, for example, I mentioned this already when I actually demonstrated in one of my classes how our internal CIT network infrastructure works. So I basically described and I showed a few people how it actually works. So all the computers inside a CIT classroom, they are connected to a central switch, which is located on the top shelf of our server rack inside of the labs. Now that switch is basically a switch that connects all the computers within the classroom, but there is a link that goes from this specific switch and connects this switch to the data store that we have, in other words, to our internal server. Now, I don't know if you guys noticed, but all the connections that goes from every single one of the machines to the switch, they are all gigabit Ethernet links. So they are all Ethernet cables connected to the switch and to every single one of the client computers, every single one of the end stations, every single one of the lab machines. Now, I don't know if you guys noticed, but the link that is the link that connects the switch to the server room, it's not actually an Ethernet cable that does that job. It's actually a fiber connection. It's a multi-mode fiber. So we just basically have two strands of fiber that connects that specific switch to our uh, internal CIT's network. Okay. Is that clear? Now, in other words, someone at some point when designing CIT's ICT internal network infrastructure, they had to consider the users that were going to try to access the data stores. They had to consider the bandwidth. In other words, most of you guys in the beginning of the semester, you actually have to reimage your hard drives at the same time. During the semester, most of you guys also have to access the files and services at the same time. So that basically means we have a higher bandwidth requirement to the server itself. And that is because the link between the switch from every single one of the classrooms to the server is the link that would expect a higher traffic flow from the user communities. In that case, it could be the students user community, which is just basically you guys trying to access the services, the applications, the images that we have stored in our Norseman server. Okay. Hopefully that's clear. So if we have no more questions, let's move on. So traffic flow. Now, measuring traffic flow behavior can also help us as network designers and network engineers to characterize the behavior of existing networks. In other words, we understand how the traffic flows, we understand and we can categorize the network much, much better. We can explain these type of things that I just explained to you guys. So if you understand this, you'll be able to basically go to a certain place and understand why certain link is a fiber link, why certain link is an Ethernet link. Now, if you are hired, for example, to make sure you can upgrade a network, you can basically use your critical thinking to basically try to find out if the best decisions were made when a certain network was designed or installed, and then you can work it out, the improvements that can be made. Now, another thing which is good for our uh, measuring traffic flow is basically that it allows us to plan network development as well. So if we are considering an expansion in the future, if the company wants to expand and have fewer more users in the nearby future, if we can categorize the user communities, we can categorize the data stores, we can categorize the existing network infrastructure, we can basically plan ahead of time. We can tell the client or the customer if that's going to be possible, how much the network needs to grow in order to accommodate the extra users, and so on and so forth. Now, it also helps us quantify network performance. Now, we understand these user communities, we understand the data stores, we understand how the traffic is flowing in our network. It also helps us to basically measure the performance, analyze, and come up with ways we can improve the performance as well. And it also helps us refer to the usage of the users and applications. If certain users are using and consuming too much bandwidth, and we basically need to limit the amount of bandwidth for certain users in order to have a better quality of service to other users. So it's all related to this, and it's all related to the way that we can optimize the services in a way that we can optimize a network to a client. Because after all, guys, we need to face that the most important thing as a network engineer is to make sure everything gets what they want, pretty much. So if someone wants to have access to the internet quickly, we need to try to make sure we can do our best to meet the goals and accomplish that. All right. Okay. Now, traffic flow. Now, there's a way we can actually describe traffic flow as well based on the amount of bits per second that is traveling across a link. That would just basically help us with the optimization of the network, and that is also going to help us understand what can be done to improve network performance. Now, when we're characterizing traffic flow, there are certain things we need to check. The first thing is basically where the traffic is coming from and where the traffic is going to. So if we understand where the traffic is coming from, where the traffic is going to, we can basically characterize the traffic if it's basically relying on to download or upload speeds. Now, I think this is pretty much clear to you guys, but I'm just gonna ask this quick question. So does anyone know the difference between download and upload? So it may sound like a fundamental questions. I think you guys came across this before when you're studying networking essentials or introduction to networks. How can you tell if it's download or upload? Anyone?
Download is when you're taking something from a server to your host,
Exactly.
and upload is when it's coming from your host to the server.
Exactly. So what basically dictates if it's a download or upload is the direction, right? So if you are sending a file to a Facebook server, for example, you are uploading an image, right? Because you rely onto the upload speed to achieve these tasks. Is that clear? So basically, you have a 10 megabit a 10 megabit image you want to upload to Facebook, and your upload speed is 1 megabit per second. You can just basically work it out how long it's gonna take for you to upload a certain file. Now, when you want to obtain a file from a server, you are actually downloading the file, so you'll be relying on the download speed. Okay. Now, when we're characterizing the traffic flow, we need to understand what is the source of the information, where the destination of the information is, the megabits per second, in other words, the throughput, the current throughput of the link, how many bits are actually being squeezed in the link. Now, I'm just going to do a quick review here to see if you guys remember this as well. The difference between bandwidth and throughput. Does anyone remember? Sometimes these two terms, they are used interchangeably, but they are not actually the same thing. Does anyone know the difference between bandwidth and throughput?
Was bandwidth the theoretical max and throughput what it actually achieves?
Exactly. So in other words, the throughput is actually something you can measure. Okay. So the throughput can be measured. So if you have a traffic flow analyzer that will be able to help you measure the amount of bits per second being transferred, that would be your throughput. Okay. Now the bandwidth is theoretical. It would be the maximum amount of bits per second you can squeeze into a certain media, but that's not necessarily going to be the case. Okay. So it's not guaranteed it's going to be that value. For example, if you buy an Ethernet cable, you can buy many standards of Ethernet cable. You can buy a Cat5 or Cat5e. Cat5e, for example, is up to 1 gigabit per second bandwidth. Now, pay attention to this 1 gigabit per second bandwidth. And why am I referring to this 1 gigabit per second as bandwidth? Because that would be the theoretical amount. Okay. It doesn't mean everywhere you have a gigabit Ethernet cable, you are necessarily going to achieve 1 gigabit per second. Of course, that would be the maximum limit. So if you have optimal circumstances, you're probably going to be achieving 999 or something very close to 1 gigabit per second. Now, if you talk about the throughput, that would be the actual screenshot in time of the amount of bits per second being transferred at that specific moment. Is that clear? So when we characterize this, the source, the destination, the throughput in the link, it also helps us determine if we can optimize the network, if we need an upper link that needs to be faster, and so on. This is a traffic flow example. It's just basically taking into consideration everything that we studied so far. Now, this network is basically separated based on the user communities. As we can see here, we have a few user communities. We have administration user community, business and social sciences, math and sciences. We also do have arts and humanities, and we have library patrons. We have 30 Macs and 60 PCs, the amount of PCs on every single one of the user communities as well. Okay. Now, once we determine the user communities, we can also determine where the data stores are. Now, can anyone identify where is a data store in this network? An internal data store in this network? Where is it located? Anyone? It's in the library, so we basically have a server which is located in the library. Congratulations for those that got this. So we have a server farm located in the library. This server farm will basically have information, will have data. They will store every single information that wants to be shared between the computers, between the machines. Now, if you guys have done manage desktops or NIA, and you had to share certain folders from a server, and you had to configure a DFS file system in order to store certain files, certain folders, that would be located in the server farm. So basically, every single one of the users, they are in a domain environment. Most of the time they want to access a certain resource which is shared amongst them. That file would be located in the server farm, in other words, in the data store called server farm. Now, in this case here, everybody could be trying to access the server farm for a certain file at the same time. Now, if you're making decisions based on the links here, which one of the links, let's say you have this switch in the middle, which is connecting the server farm to the entire network. You only have one fiber connection that can be used in this switch. Let's say you only have uh, one port on the switch, which is a fiber port, and that is a 10 gigabit per second port. Now, would you use this port to connect uh, any one of these switches, or would you reserve this port for the server farm? What would you think would be the best choice here? See if you guys get this. Reserve for the server farm, that would be the most obvious solution, and that's just basically because if all these guys, they try to access a certain resource in the server farm, they need to be able to have a nice bandwidth or theoretical amount that they can reach, especially if all the traffic flows, they are going out the same interface. Okay, so you see the similarity here when we actually designing computer networks, and we actually, when someone is designing roads, and someone is designing uh, uh, our real traffic, when we're going to drive our cars and we're going to go to the traffic. So when someone designs this, someone in access camera, for example, starts drafting everything, how the roads are going to look like and where they're going to merge together in order to form another one, they need to consider this. They need to consider where are all the traffic coming from, where is all the traffic going to, where do you need to have a wider road, a wider street, an avenue, and so on and so forth. It's similar here. So keep this in mind anytime you actually need to design a network such as this. Now, here we also have a connection to the internet, which is just basically represented by this Metro Ethernet to internet connection. It's a 10 megabit per second. Now, if you thought that reserving the fiber optic link to connect everybody to the network, to the internet, would also be a good idea, I'm going to tell you why this is not that of a good idea. And in order to do that, we need to understand the traffic flow, right? So if all these guys at certain point in time, they will have to access resources on the internet, they will all have to go out this way, correct? So they all have to go to the router first, and then they have to go out to the internet. Now we have a limit, we have a bandwidth, which is 10 megabits per second for the Metro Ethernet link, correct? So the maximum amount of bandwidth I have here is 10 megabits per second. Okay, so our internet connection is not gonna be higher than 10 megabits per second. It's unlikely this is going to happen, okay? And that is basically because when the ISP offers you the plan and the plan is attached to your contract, they will basically limit the amount of bandwidth on the router that connects your ISP router to the internet. Okay, so they will basically set the hard limit. Your router won't be able to transfer more than that. Okay, now if you thought that reserving the connection to the router to be the fiber link, in other words 10 gigabits per second, that would be such a bad design decision. Can anyone tell me why that would be such a bad design decision? If I configure the link to the router to be a fiber optic link, I'm going to spend way more money because fiber is way more expensive than Ethernet. And my question is it necessary? Is it a good decision? And the answer might surprise you, but come on. Any opinions? Does anyone think that configuring this link to be a fiber link would be beneficial? Anyone? Some people saying no, some people saying no. Now, my answer, guys, is actually depends. Okay, it depends. Like if you see that there's going to be an upgrade to NBN in the nearby future, that would be a good decision because then you don't have to replace the link, right? So if you know there is going to be an upgrade coming soon, I don't see any problem with it. Now, if there's not gonna be any upgrade coming up soon, and you know that there is this limit here in the uplink to the internet, there is no reason why you would spend much more money with the link connecting to the router, and that is because no one is gonna be able to take advantage of that. No one. Okay? Now, there is one exception here, and if you're not doing routing and switching, I don't feel too much pressure because you don't know this. But if you're doing routing and switching, you also know that there is something called inter-VLAN routing, correct? So according to the diagram here, we have layer 2 switches. Okay, that means if we have VLANs across the network, we're also relying on the link to the router in order to make the routing decisions between the different networks, correct? Now, if you also have inter-VLAN routing here, that would be a good decision as well. Because remember that in inter-VLAN routing, this link will be carrying traffic for all the VLANs. So there will be a lot of traffic flow going in to this router interface, going out of the router interface to another VLAN, coming in again from another VLAN, going out again the same interface to another VLAN. So if that's the case, if inter-VLAN routing is also something in your network design, that would also be something to consider as well. Remember, guys, we need to understand every single type of traffic flow in the network in order to optimally design our network. Okay, is that clear? Hopefully that's clear. Let's move on. Flow types, like we described, if we understand where the flow types are coming from and where they're going to, we're basically able to determine if that's an upstream or if that's a downstream flow. Now, if it's an upstream flow, it basically relies on the upload speeds. If it's a downlink flow, it's relying on the download speeds. We can also have certain traffic flows which are bidirectional, so that basically means they rely onto the download and upload speeds as well. So they rely onto these two things. All right, cool. Now, types of traffic flow. Traffic flow can have many types. We can have terminal to host traffic flow. We can have client to server traffic flow. We can have a traffic flow to a thin client. A peer-to-peer traffic flow would be bidirectional. Server to server traffic flow is another one, which is usually bidirectional. Distributed as well, which can be a little bit of both, and so on. Now, how about the traffic flow for voice over IP? How does it look like? Now, the traffic flow for voice over IP is associated with transmitting the audio voices, separate from the flows associated with the call setup and tear down. Now, the flow for transmitting the digital voice is essentially peer-to-peer. That's basically because whenever you are calling someone using a VoIP phone, you need to be able to listen and you need to be able to speak at the same time. It also has call setup and tear down, which is a client server flow. Okay. Network application traffic characteristics. Now, every single one of the traffics, once we define the flow and we can determine where they're coming from, where they're going to, we can also characterize them based on the application that they're related to, based on the flow, based on the protocols that are being used. Is it using TCP? Is it using UDP? What type of protocol is being used by these traffic? Okay. Is it being used by a web browser? What kind of traffic is it? Is it HTTP, HTTPS? What type of protocol is it being used? Is it TCP? In this case, HTTP is going to be using TCP, so we can describe that as well. Where are the data stores? Are the data stores on the premises? Are they located in a server farm inside of the company's premises? Are they located in a remote server which is connected to the internet and then accessible to the internal company resources? How is the traffic located? What are the characteristics? What's the approximate bandwidth requirements? So most of the applications, they actually have a minimum bandwidth requirement in order for them to work with a minimum acceptance level, and we need to find out what that amount is. Okay. And we also need to worry about the quality of service requirements, because latency is a key thing when we are actually characterizing the quality of service. Because in other words, if the traffic is delayed too much, you are not going to be able to talk using a VoIP phone, because the call just basically becomes unbearable. Okay. Traffic load. Now, to calculate whether capacity is sufficient, we should check the number of stations. We need to check the average time that a station is idle between sending frames. We need to check if the time required to transmit a message once the medium is gained. Now, studying idle times and frame size with the protocol analyzers such as Wireshark and estimating the number of stations, we can determine if the proposed capacity is enough. Now, even though you think your computer is not doing anything, now even though you are not running any application, we have something called the background traffic. Okay? The background traffic is the traffic that is necessary to keep all your services running. For example, DHCP. So if you study DHCP before, especially when you study routing and switching, you know that DHCP relies on to the expiry, right? So there's usually an expiry time for the lease. Once the lease is expired, the DHCP client will request automatically to renew the lease to a DHCP server. Now, you don't need to do anything in order for the machine to do this. It will just do it automatically. It's just a service that is already running in the background. You don't have to worry about doing this manually. Okay. Of course, you can do it manually as well with the DHCP slash release and slash renew. You can just basically force these processes to happen. But if you don't execute the command itself, the process will happen automatically after a certain amount of time when the lease is about to expire. Okay. Now, in order for us to understand what type of background traffic is happening across our network, we can take advantage of this amazing tool, which is a protocol analyzer called Wireshark. Has anyone used Wireshark before? Anyone? If most of the people here haven't used it before, we're going to do a demo using Wireshark in the end of the lecture. But basically, Wireshark will be able to help us see everything that is going in and out of the network. And by the way, we can filter the traffic in Wireshark based on everything that we want to be coming in. So if you're not interested in any traffic that is going out of your machine, you can actually create a Wireshark filter to just basically display everything that is coming to your network and not out of the network. So Wireshark is so powerful, guys. It's amazing. Now, Wireshark is super useful for cybersecurity, especially because cybersecurity professionals, they need to understand the vulnerabilities. They need to understand the services that are running that shouldn't be running, for example. They need to understand the ports that are open, the ports that are transferring information that shouldn't be opened. Uh, Wireshark help us determine the ports that we actually need to have opened in our computer in order to help us tune and improve our firewall characteristics. Now, when I was a NIA teacher, I used to get a question multiple times, and that question was, if every single prec that we do at CIT, we need to turn off the firewall, how are we going to do it in the real world environment? Now, In the real world environment, what happens is that usually network professionals, they have two environments. They have the testing environment and they have the real world environment. Now, every time we want to deploy a new service, for example, DFS, or we want to deploy Active Directory, anything that we want to deploy that is new to the network, and we want to create new firewall rules, what we do is we deploy the service in the testing environment. Now, in the testing environment, we can pretty much have all the firewalls turned off in the testing environment, because this environment is not actually the environment that everybody connects to. And this environment is usually isolated. It's usually an environment which is running into a virtual machine instance. So it's completely isolated. So if something bad happens, there's no issue, it's isolated. Now, in the testing environment, we're basically going to turn off all the firewalls. We are going to install a protocol analyzer. Most of the time, it's actually Wireshark. So we install Wireshark in this testing environment. We study all the port numbers that we need to have open. We understand the source IP, the destination IP address for the traffic flow that we need to make certain services work. And that's how, after doing the firewall configuration in the testing environment, we can then just basically migrate all the rules that we configured in the testing environment to the real world environment. So hopefully now that's clear to you guys how it works. In the real world environment, please, you are never going to turn off a firewall. Please, don't do this in the real world environment, okay? You are not going to do that. Now, why do you do this at CIT? That's just basically because you are more focused in understanding how the service works, in deploying the service itself, than actually in the firewall rules. So we just basically don't want you guys to be, banging your heads against the wall trying to find the best firewall rule to make certain things work, okay? So if you're doing in a lab environment, in a testing environment, it's okay. You turn it off, make sure everything works, and then you run a protocol analyzer, make sure you understand the traffic flow, characterize the traffic flow, create your firewall rules, and then you're good to go. Okay, sizes of the objects, they are also important. So if we're going to understand the traffic flows, we're characterizing the traffic, we also need to understand the size of the objects that will be downloaded or uploaded in our network. That will help us determine the amount of time that is necessary to upload a certain file, to download a certain file. Here in the screen, I have a few examples of the sizes of common objects, of common data information that we find uh, in our computers nowadays. We have the terminal screen, which is usually 4 kilobytes, so it's not demanding at all. You can even do a terminal screen even if you have a dial-up connection. Dial-up, guys. Um, Simple emails, they are usually 10 kilobytes without any attachments. Simple web page, they are usually 50 kilobytes in size. Now, I remember back in the days, those more complex websites with a few more images, they are way above 50 kilobytes. So if you guys started using the internet when it was still dial-up, or uh, the infancy, the beginning of ADSL, you remember that even when you open uh, a web page, uh, that would be extremely slow to load the web page. That's basically because the web page content was still being downloaded. And if you remember, the dial-up maximum bandwidth was 56 kilobytes per second. So sometimes it would take a few seconds in order for you to be able to display the content of a web page. Now, high quality images, they range, but they're usually around 50 megabytes, so 50,000 kilobytes. Database backups, they can be in the order of gigabytes, so or even more. Now, just out of curiosity, some PC games, they are highly demanding, so they require a lot of bandwidth. Usually the Fortnite PC game is a little bit over 18 gigabits per second, so good luck trying to download that if you have a dial-up connection. Okay? It's gonna take your entire life to do this. Okay, traffic behavior. Now, traffic behavior is also important. Now that we understand where the traffic is going from, where it's coming from, where it's going to, we can understand the behavior. Now, we have many types of traffic. We have the unicast traffic, which is just basically when we want to send traffic from one machine to another machine specifically. We have the broadcast traffic, which is when we want to send information from one machine to multiple machines in the same network. And if you remember this, broadcast traffic is usually something we want to avoid in our network. And why do we want to avoid broadcast traffic? Because it uses huge amount of bandwidth. Okay, it disturbs every single PC in the broadcast domain, every single machine connected to the same network. Okay, in other words, it has the same network portion, the same subnet mask will be disturbed because they will receive the traffic, they will check the broadcast message, even if they're not interested in that traffic, they had received it already. Okay, so it wasted bandwidth already. Okay, even though they can discard the traffic because it's not interesting to them, you still consume the resources. You still had to forward the frame on a switch. You still had to forward the packet. You still had to do everything. Okay? You still had to do the encapsulation, decapsulation. So you wasted resources. Okay? Now, we already studied this, but one way we can avoid the broadcasts is by segmenting the network, creating the VLANs. Now, there is another way we can improve the traffic by avoiding the broadcast traffic, and that is by having multicast instead. So instead of everybody in the network being able to receive, we are just going to tell if we want to receive or not. Okay? And that is part of the multicast traffic behavior. In a multicast environment, only certain people that are interested in the traffic will receive the message. Okay? Not everybody. Okay? Now we call this group that is interested in receiving the multicast group, the, the multicast traffic, the multicast group. Okay? So all the multicast group members, they will be the ones that will be receiving the network multicast traffic. Network efficiency. Now that we understand user communities, we understand data stores, we understand traffic flow, we understand traffic characteristics, we understand traffic behavior, we need to understand how we can use all of this to make our network more efficient. Now, when we're also building a network which is more efficient, we need to make sure we understand the frame size, the protocol interaction, how the protocols interact to themselves, what is the minimum and maximum frame size to make sure everything works accordingly. We need to understand windowing and flow control, if the amount of traffic being sent needs to be reduced, and we also need to understand error recovery mechanisms. Quality of service. Now, IETF, Integrated Services Working Group Specifications. So we have three specifications for quality of service. The first one of them is the controlled load service. It provides client data flow with the quality of service, closely approximating the quality of service that same flow would receive on an unload network. We also have the guaranteed service, which provides a mathematically probable bounds on end-to-end packet queuing delays. Now, the one we are actually interested is this one here. This is the one which is the most common way of doing quality of service. It's using the IP packets header called the DSCP, Differentiated Service Code Point. Now, this DSCP will just basically be a header in our IP datagrams, which will basically dictate the behavior of the traffic. How should a router deal with the packet, if it should give it precedence, if it should not give priority to a certain packet. All of these routing decisions on a per hop behavior will be done considering the DSCP header in our IP datagrams. So we can basically tell that a packet should be higher priority than other packets. In other words, every time a router receives a packet like this, it will just basically forward it quicker than anything else. This is a summary of everything we studied today. So um, continue to use a systematic approach, so a top-down approach, because after all, if we understand the OSI layer model, if we understand how traffic flows from one machine to another machine in our network, we are basically going to be able to understand how things work, and we are basically going to be able to make everything in an optimally way. We're basically going to be designing everything that works as it should be. Now, do not select products until you understand the network traffic. Guys, don't go shopping before you do your homework. And now, doing your homework is basically doing everything that we described in this session. Understanding what type of traffic we have, understanding what type of load, and understanding the requirements for every single one of the links, understanding the theoretical bandwidth that would be required by every single one of the applications, understanding where the data stores are, understanding the characteristics of the traffic, and so on. So if we don't do this first, we can basically spend thousands and thousands of dollars with equipment that we don't even use, okay? That we don't even need to make everything work accordingly, okay? Now, a company that doesn't have a data store locally, that only has 20 employees on site, doesn't need to have a $50,000 200 port switch. Just an example here. Okay. But this is not necessary. We need to understand the client, the customer needs, the traffic flow, the user communities, the data stores, and everything else before we go shopping, before we start selecting the devices, start selecting the technologies, and so on. We have a few review questions, so if you guys want to do them, that would be awesome. You need to list and describe 6 different types of traffic flows. You also need to say what makes traffic flow in voice over IP challenging to characterize, and also why should you be concerned about broadcast traffic. So please take a few moments in order to try to answer these questions. And this is pretty much all we had to cover today.